This is the second of 2 lessons on using the Sharp scientific calculator for technical math. I'm using the Sharp ELW516XG calculator. The first lesson showed the regression of linear and semi-log data sets. In this second lesson, we'll look at the regression of other types of data, namely inverse, quadratic, power, and exponential regression. And you'll be shown how to use the calculator to solve linear equations, polynomials, and differentiation and integration. Now, the procedure for entering and retrieving data in regression was shown in detail in the first video, so I won't repeat it here. However, I will show you how to enter and retrieve data into these last 4 linear polynomial equations, differentiation, and integration. Let's start by looking at page 242 in the notes. This is page 242. I have a data set that describes the relationship between pressure and volume of a gas. We know this follows Boyle's law for ideal gases, and it should be inversely related. So I'd like you to enter this data into the inverse regression mode of your calculator, and that'll be stat 6 mode. Y equals A plus B over X. Please enter the data on the Excel sheet that's on Blackboard. Let's take a look at that. So here it is on Excel, the same data. I've also given you a couple of samples or unknowns to solve for. So enter the data into the inverse regression mode of the calculator, and then retrieve the regression coefficients of the equation, and forecast the x prime values, the y prime values, and the unknowns. Then come back and take a look at this, and I'll show you the answers and we'll talk about it. So you've entered the data in the spreadsheet from your calculator, and take a moment to look over the results and see how well the forecasts of x prime and y prime fit the actual measured values. So some of it's not bad, some of it's off a bit. Let's plot a graph for the data and take a look at that. Let's select x and y values, go to Insert, a scatter plot. We'll choose points without lines. If you choose Quick Layout number 1, that'll give us placeholders for the axis titles and the chart titles. Click once on the axis title to select it. Click a second time to see the flashing cursor. Then you can type Control-A from the keyboard to select it all, and then you can type in easily. We'll call this one P, pressure in centimeters of mercury. And the y-axis would be V in milliliters. The axis title, how about P versus V? We don't need the legend. Let's get rid of that. Right click on any of the points and we'll add a trend line. Now you notice we don't see an inverse trend line function here. Even though we know that pressure and volume is inversely related, well, what are we going to do? Exponential, not a very good fit. Logarithmic, not so good. Polynomial, not at this point. Power function appears to give a very good fit. Let's try that. Display the equation, display the r squared. Okay, take a look at that. Notice that the r squared value, 0.9997, is even better than the r squared value for the inverse relationship from the calculator. What's that mean? Is there any similarity between the power function equation and the inverse function equation? Look at the power function equation. Y is equal to A times x to the b. Now consider the case if b were equal to -1. The power function equation would become y equals A times x to the minus 1, or y is equal to a over x. And that's pretty similar to the inverse equation y is equal to b over x plus a constant a. So the power function equation can fit inverse data considering that the index b can be -1. So it would seem that the inverse function is merely a special case of a broader function that we call the power function. So we'll take it as if it's inverse, and we'll talk about the power function later. So let's go back to our data. I can't help but notice how poor the forecast is. For a y value of 10, the data, the observed data, the measured data was 130 centimeters of mercury, but the forecasted is 164. It's a very large error. Why would that be? The r-squared is not bad. 9991 is pretty good. But look at the graph. So when y is 10, we're talking about way down here close to the x-axis, where the curve is almost asymptotic. So you can probably appreciate that a slight variation in y could make a huge variation in x, drives us way out here. And this is just an inherent problem with trying to interpolate a graph or data that's asymptotic if you're in that region. In the center region, we can expect a much better forecast. And in fact, we do see some pretty good values here in the middle range that are acceptable. Obviously, a better r-squared would give us better fit. Let's scroll down, and I'd like you to repeat the process of obtaining intercepts and forecasting, this time in Excel. Now, Excel doesn't have a function that forecasts inverse relationships, at least none that I'm aware of, but we can linearize the data and then use linear regression. And we can linearize the data just by taking the inverse of x, plot the inverse of x over y, and let's see how that goes. So this will be equal to 1 divided by x, enter. Here are the inverse values. I can probably drag this right down to here. So let's plot the data for the standards, the measured values. The first 1, 2, 3, 4, 5 data points. Let's plot that and take a look at it. That'll be insert a scatter plot, just points. Notice how linear that looks. Okay, let's choose quick layout. Number 1, what do we call this? The x value, it'll be 1 over p. That'll be centimeters of mercury to the minus 1. And the volume is still the volume. Our chart title will be V versus 1 over p. I'll get rid of the legend, delete. Now let's add a trend line. We're going to add a linear trend line this time. That looks pretty good. Display the equation, display the r-squared. Same regression coefficients. Looks like the same RSQ value as we saw from the calculator, 0.9991. Alright, so that looks like a good fit. How can we then forecast our x and y prime values? So first we better get our regression coefficients. So we can get the slope. Now we could fetch it from the insert function, but let's do it differently this time. We'll just say equals slope, tab. The known y's will be these first 5 y values, comma, the known x's will be our 1 over x values, not the x values. 1 over x is linear. 1004.9, same as the one above. How about the intercept? Notice above here I called it an asymptote, but now it's actually an intercept. Equals intercept, tab, the known y's, comma, the known inverse x values, enter. 3.855 looks the same as the inverse relationship data, and r-squared equals RSQ, tab, known y's, comma, known inverse x values. All right, so now that we have the regression coefficients, we should be able to write equations. It'll be pretty straightforward for the y prime values. Y is equal to a plus bx. That'll be a, f4 for absolute reference, plus b is a slope, f4, times the x value, which is going to use 1 over x here. Enter. 11.6, that looks good. And we'll drag this down. All right, so those are good forecasts. Now what do we do for the x prime values? We have to rearrange the equation. So to solve for x, we'll choose the equation x is equal to y minus a over b. So we'll start right here. Equals bracket. Here's our y value minus the intercept, f4 for absolute reference, close the bracket, divided by the slope, f4, enter. Okay, that doesn't look like our x, but you see what we've actually forecasted was the inverse, because that's what we entered into the data. We entered 1 over x. So here we'll take the inverse of our forecasted value, and there we are, 164-ish. All right, so what are we going to call this? Well, this is actually 1 over x that we forecasted here. So I'll change this to 1 over x, and this will actually be x. All right, so we should be able to drag these down. How do they look? Yes, 99, 53, and so on. All right, let's forecast our unknowns. For a pressure of 25 centimeters of mercury, the inverse value is 0.4. To calculate y, it's equal to a plus bx equals a, the intercept, plus the slope times our x value. We're using the inverse of x, and that's 44.0. Notice I didn't bother with absolute references because I'm not dragging this value. How about forecasting the x value that corresponds to a measured volume of 150 milliliters? We'll use the equation x is equal to bracket y minus a, our intercept, close bracket, divided by b, the slope, enter. That's the inverse value of x. To get the actual value, it'll be equal to the inverse of that number, 6.9. How does those look? Yeah, pretty close. Okay, so there's a way to handle it on the calculator as well as Excel. So what we've seen here is a really important technique. Linearizing data such that we can use linear regression is very useful. Later, you will see how important this technique is when we calculate an uncertainty or standard deviation associated with a forecast. It's very straightforward for linear data. It's very complicated for nonlinear data. So being able to linearize data can make life a lot easier for us in the long run. Regression of quadratic data. On page 241, I have a data set that I would like you to enter into the quadratic regression mode of your calculator. That would be stat 2. Quadratics have the form y equals a plus bx plus cx squared. I just want to caution you that when you use the quadratic formula to solve for roots of a parabola, the equation they use is different. Recall that a is the coefficient of x squared and c is the constant. But in statistics, it's done as you see here. A is the constant, b is the coefficient of x, c is the coefficient of x squared. Let's go to the spreadsheet and take a look at this relationship. This is in the Calculator Lessons workbook, and it's on the tab marked Quadratic. The data I have is for this instrument. It's called a flame photometer. It's like the baby brother of a flame atomic absorption spectrometer. It uses a low temperature flame. It's a relatively inexpensive instrument. You aspirate a sample into the flame and metal cations are excited and they emit photons and the detector senses it. It works for metals that are easily ionized, like the alkali metals, lithium, sodium, potassium. Here's a data set. This is the emission intensity as measured by the photometer. Here are the concentration of the standards, and here is the emission of an unknown sample. So I'd like you to enter this in the quadratic regression mode of your calculator, and then forecast y prime and x prime and all the rest that you see here in your sample, and get as much as you can information here. When you do that, I'll come back and we'll talk about what this means, and we'll work on it in Excel at the same time. So I trust you've had an opportunity to enter the data into the quadratic regression mode of your calculator and then forecast the x prime values and the differences between the forecasts and the measured values and the percent differences for the x and the y, and then also forecast the unknown values. Some of you may have not been able to obtain the r-squared value. Some of the earlier Sharp calculators don't give it for a quadratic, but the newer one that I'm using does, so you don't need it at this point. You can look at your data and say, how do your forecasts compare to your values? They look really good, don't they? Check it out. So if this, let's make this 500, move the decimal over 2 places, this becomes 508. So you're out 8 parts in 500, which is less than 2 parts in 100. So less than 2% is good. Likewise here we out 0.5 parts in 100. That's very good. And this likewise, these are very close indeed. So the forecasts look excellent. So even if I didn't know the r-squared, I could calculate my unknowns with some confidence that they're probably correct. As long as your standards are accurately prepared, then your forecast should be accurate as well. So now I would like you to solve this in Excel. If you scroll down a bit, and let's start by generating a graph. Select x and y values, insert a scatter plot, just points. We'll choose quick layout 1. The x-axis, we'll call it sodium ion. I'll just say sodium, that's ppm. The independent variable on the x-axis, and this will be intensity on the y-axis. This will be intensity versus concentration of sodium in ppm. I can dispense with this legend since I only have one series on the graph. Let's right click on any point and add a trend line. I want to choose a polynomial. You'll notice there's higher orders. You can go 3rd, 4th, 5th, up to 6th, but we always want to use the lowest possible. You'll appreciate why later. And we saw that the r-squared was very good for a quadratic. That'll be more than adequate. Display the equation, display the r-squared. Now, we don't have any method currently yet. We will later, but we don't currently have any method for a function in Excel that would give us the coefficients of the equation in cells that we could copy and paste. So we're going to have to copy them, transpose them, if you will, type them in by looking at the graph. So the first thing we want to do is give this more decimal places. We see we only have 1 sig fig in this coefficient of x squared, and that's in the 4th decimal place. So if we just have 1 sig fig, we're limiting our accuracy. Let's give it more sig figs. So let's right click on this and go to format the trend line label, and we'll change the category to number, and I'm going to give it 6 decimal places. And now at least I have 3 sig figs in my coefficient of x squared. So we'll have to very carefully copy the coefficients c, b, and a. Notice c is negative term, so let's be careful with that. So c is negative 0.000141. B is 0.012798. And A is 0.000607. Enter. Let's just double check that these are correct. All right, now we can use these coefficients to build an equation to solve for y. And we'll use the equation, I'll just follow it as it's written here in the chart to make it easy to follow. Equals C F4 times x squared plus B F4 times x plus A F4. Enter. Let's see how we did. Good. Okay. Take some care, eh? Well, that's kind of cool, but the problem is how do we forecast the concentrations? That's what we're really interested in, right? We measure the intensity of standards and unknowns and want to measure the concentration. Well, at this point, we really have no way of doing that. Later on in this course, I'll show you how to handle polynomials in Excel, obtain the regression coefficients, and forecast x prime. We'll do that a little bit later on. Next to linear relationships in chemistry, quadratics are probably the second most common relationship we encounter. We see it in physics as well, so it's something we need to learn to deal with, and we can handle it in Excel with some tools that I'll give you. The next data type that I want you to perform regression on is called a power function, y equals a times x to the b. Now this information is not in the notes. This exercise is only in the Excel file. Later in the notes there's an explanation of some of the theory behind it, as I'll explain later. So we'll just work here in the Excel spreadsheet. So what I'd like you to do is enter the x and y values into the power regression mode of your calculator, Stat5, and then complete the forecasts and percent differences and the coefficients. Just before you go there, let me give you a brief explanation. You're probably aware that when you turn a garden hose on a little bit of pressure, the velocity is low. But if you increase the pressure on a fluid, it moves faster. Kind of somewhat illustrated in these diagrams. So there is a relationship where increasing pressure increases velocity of a fluid. But the relationship is not linear. Just look at the data. In order for the velocity to increase by a factor of 2 from 10 to 20 feet per second, the pressure that's applied has to increase approximately a factor of 4 times. This is a unit of pressure. It's feet or height of water. The height of a water column is a common unit for pressure. But you can see it's not linear. It does fit very well to a power function. So go ahead, please enter that in your calculator, and we'll come back and talk about it some more. So presumably you've had a chance to enter all the data in your calculator and forecast the results. And what's this data telling us? Are the forecasts good? Well, yeah, look at a velocity of 20, forecast at 20.6, 30 at 29.8. These are very close. Look at the percentage differences. Only one above 2%. Very good. Pretty good on the y prime side as well. So this is good data. The r squared is 9993. What about the unknowns? So with a velocity measurement of 15, what's the forecasted pressure? We get about 3.6. Does that look about right? Between 10 and 20, yeah, it should sit between, say, 2 and 6, and it is. And for a pressure of 15 feet of water pressure, we're forecasting about 31 feet per second. If we look down here, here's 14 feet of pressure at about 30, so that looks about right. So this looks pretty good overall. So how are we going to handle this in Excel? Let's start by plotting a graph. Let's plot x and y for the knowns. insert a scatter plot, lines only. We'll choose quick layout number 1. Axis titles. Velocity in feet per second on the x-axis. On the y-axis I've plotted pressure in feet of water. And so this graph would then be titled y versus x, pressure versus velocity. So the rule is in technology, a graph is y versus x. This is pressure versus volume. Now normally you put the independent variable on the x-axis, and you could argue that by increasing the pressure I am increasing the velocity, and so pressure is the independent variable. I chose to plot it the other way because I have velocity values listed as x. Now I could argue that it could be because when you stop a fluid, its kinetic energy transfers to pressure. So it could be that the pressure we're talking about is created by the velocity. So in that regard, we could say velocity is the independent variable. On the y-axis, I see Excel has given us some decimal points. There's really no reason for this. Always use the minimum possible precision on an axis. We're not trying to read the graph, and it just clutters it. So just select the y-axis, right-click, choose to format the axis. Down near the bottom we see number, and we'll say number of decimal places. We don't need any on this axis. Say 0 and close. Tidier. Okay, let's right click on a point, add a trend line. We're going to add a power function, display the equation and the r squared. And this looks to be about what we got from the calculator, so that's good. So now how are we going to use Excel to forecast values? We don't want to have to type in these coefficients of the equation. That's tedious and prone to error. Is there a way we could get Excel to generate the coefficients of the equation so we could copy and paste from cells? Well, one of the ways we could do this is to use a little bit of algebra. So look at the equation, the power function. We could take the ln of both sides, or the log. I'll choose the ln in this case. And that'll be the ln of y is the ln of a times x to the b. I know that the ln of a product is the sum of the lns, and so I have ln a plus ln x to the b. And I can write ln x to the b as b ln x. And so when I expand this, I get ln of y equals ln of a plus b ln x. So this sure looks like a linear equation. Y equals a plus b times x. In fact, it is. This should fit very well to a linear regression if we first take the ln of x and the ln of y and plot that. Then we can get a slope and intercept. In fact, why don't we do that, and we'll plot the graph and see what it looks like. So ln of y equals ln tab y value, enter, and we'll scroll down. Same for ln of x equals ln of x values. Okay, let's plot the ln of x and the ln of y and take a look at that. So to enter non-adjoining data, hold the control key down while you drag over the second group of data. Insert a scatter plot. Looks pretty linear, doesn't it? Quick layout number 1. Now our x-axis will be ln velocity, and the y-axis will be ln of pressure. I'll just leave it at that. So our chart title will be ln pressure versus ln velocity. Get rid of the legend. We're going to right click and add a trend line, and we'll make it linear. Display the equation, display the r squared. Looks real good, doesn't it? Now look at our axes. We're off the side of the graph. We should change the values of the x-axis. Get rid of this dead space in our graph. So we'll have the minimum x value at 2, and we'll also get rid of all these decimals. We'll keep one decimal in the x-axis. So format the axis. We'll set the minimum value to 2, and we'll change the number of decimal points to just 1. And on the y-axis, let's just keep 1 decimal point as well. Select the y-axis, right-click, format the axis, 1 decimal point. That tells us we should be able to accomplish it in this fashion. Let's get the intercept and slope of our linearized data. Equals intercept, there it is, of the ln of the y values. We want linear data, and the ln of the x values. The slope will be equal to the ln of y and ln of x. And the r squared ln of y, comma, ln of x. So I see 0.9993, same r squared. Our slope is 1.99 again, but the coefficient of a is now a ln term. We're going to forecast ln y prime. So here, ln y prime will be ln a plus b ln x equals the ln of a, f4, plus b, f4, times the ln of x, which is way over here. Enter. 0.47. So take a look at the data. The actual ln value is 0.44. The forecast is 0.47. These look reasonably close. We probably did this correctly. Now we want to forecast the actual y value. Well, that would be the anti-ln of ln y. That'll be exp is the function, the exponent of the ln y. 1.60. How does that look? Yes, it looks pretty close to our original y value. I'm going to leave this undone. We saw it in the previous case. It shouldn't change at all. The y minus y prime and percent difference. Let's forecast our ln x prime values. There'll be ln of x is equal to ln of y minus the ln of a divided by b. So that's equals ln of y is over here, minus the ln of a, which will be a constant, so f4, close bracket, divided by the slope, f4, enter. 2.29 versus 2.3 looks reasonably close. Let's get the anti-ln equals exp of this value, enter. 9.9 instead of 10, those look all right. So there we go, looks pretty good. And finally, let's forecast values for our unknowns. An x value observed of 15, how do we calculate the y value? We're going to need to actually use ln of x rather than x, and then we can forecast ln y prime and y prime. Just copy those down. How does that look? With a velocity of 15 lies about here. It should have a pressure between, say, 2 and 6, and that's what we come up with. Looks all right. All right, let's forecast the x prime value for this given value of a pressure of 15. So we're going to need the ln of this value, and we'll forecast from there. We should be able to just drag these two down. How do we do? So for a pressure of 15 feet of water pressure, we're saying the velocity be 31. How does that look? 15 feet of water pressure looks about right. All right, so that's it. That's how we can handle a power function in Excel. We can linearize the data by taking logarithms of both sides and treat it as a linear regression problem. Sounds great. The last type of data that I'd like you to fit to regression is exponential regression. This instrument is an electric thermometer, and this is a metal oxide probe. As its temperature increases, the resistance of it decreases, and it's exponentially related. Now you have to actually plot the Kelvin temperature versus resistance to get a good fit of data. That is, you need an absolute temperature scale. Now in the calculator, there are actually two modes that handle exponential data. Mode 3 is the Euler exponential regression mode, y equals a times e to the bx. And in the newer calculator, they also have a stat mode 7, which has a general exponential regression mode, y equals a times b to the x. Either one of these will take the data and give the same results. You can pick whichever one you like. Perhaps you can fill in the sheet, forecast the unknowns, and get the regression coefficients, and we'll talk about this. So here are the results from the exponential regression exercise. I entered the data into both stat 3 and stat 7. In either case, the results forecasted pretty much identically. The coefficient A was the same in both cases. The index B is different, but R squared is the same. How does the data look? Actually, I'm surprised at how good it looks. The percent differences are quite small, considering the R squared is not all that great. 0.9983 is nothing to write home about. It's decent, but not excellent for sure. How did your unknowns work out? For resistance of 12 ohms, we calculated 322 degrees Kelvin. Does that look right? Let's see, 12 ohms would be about here. Yeah, it's in the range. And for a temperature of 20 degrees C, or 293 Kelvin, it calculated to be 29 ohms. 293, it's about here. It looks right. Okay, so let's go ahead and plot this data in Excel and see what it looks like in Excel. We'll select the X and Y values directly. Insert a scatter plot, just markers. Quick layout 1. X-axis title. These are temperatures, Kelvin. And the y-axis, this is a resistance in ohms. And the title will be resistance versus temperature in Kelvin. Alright, well, let's get our graph so that it data covers most of it. Let's change our minimum x-axis to say 250. Try that. I don't think we need any decimal points either. Right click, format the axis. Let's change the minimum to 250. And the number of decimals on the axis, we'll change that to 0. On the y-axis, looks okay, but I'm going to get rid of the decimals as well. Sometimes Excel puts them back in. Don't need the legend for only one data set. Right click on a data point, add a trend line. Let's try an exponential. That looks good. Equation and R squared. So the coefficient A is the same as what we got from the calculator, and we see that Excel is using the Euler exponential regression form. Here's the index B. All right, so that's easy. What about in Excel? How do we handle this in Excel? Well, one of the things we can do, as it turns out, if we plot the ln of y versus x, that'll linearize the data. Let's prove it, and then we'll come back to the formula. Take the temperature, hold down the control key, select a non-adjacent group. Let's insert scatter plot. Wow. Well, it does look linear. All right, for the minimum x-axis, what do we try, like 270, something like that? See what happens. Excel likes to keep the origins on the plots. And the number, let's see, how about no decimal places? That worked. We need quick layout number 1. X-axis title, that was temperature in Kelvin. Y-axis title, that was resistance in ohms. And the title of the chart is R versus T. I'll put kelvins in here because there's other common units. Let's get rid of our legend. We will simply right click, add a trend line. This is going to be a linear trend line. There's the equation and R squared. And they look about the same as we saw. The 0.9983 looks quite familiar. So that certainly works. If we take the ln of the y values versus x, it's linear. Let's look at the equation here. So we have y equals a times e to the bx. If I take the ln of y, then I can say, well, since y is this, let's take the ln of this term. That's the ln of a product. It's the sum of two lns. So we have ln of a plus, now ln to the base e of e is simply whatever is to the right of that, and that's b times x. And this looks like the equation of a straight line. The ln of y equals ln a plus b times x. That looks like y equals constant a plus slope times x. And that's why it works. We'll be using this to solve for ln of y, and we can use the ln of y values to solve for x. We're going to need our regression coefficients for the calculations. Let's get those. So the intercept equals intercept, and we'll take the ln of y for the y values, and the x values are the Kelvin temperatures. That looks about right, doesn't it, from the graph? For the slope, we'll have the ln of y, comma, and our x values. And that looks familiar. And the r squared, ln of y, comma, x values. Right, so now we can use these. Our equation is ln of y equals ln a plus b ln x. So I'll put here equals. Now ln of a is a constant, so that'll be f4 plus our slope, which is also a constant, f4, times x. We can drag that down. Well, the ln of y forecasted look like the ln of y measured value. That's a good indication. So the y values will be the exponent, that is e to the ln of y values. And those numbers look like the y values. I won't bother to fill in the y minus y prime, etc. We did that in the previous exercise, and we saw they were pretty good. Let's just finish this up. How do we get x prime? X would be equal to ln of y minus ln of a divided by b. So equals bracket. The ln of y is way over here. Subtract the ln of a, that's a constant, so absolute reference, f4, close a bracket, divided by slope b, which is also a constant, so hit F4, enter. That looks favorable, and that should drag all right. Good. So we forecasted x prime and y prime. How about our samples? Let's forecast the resistance that corresponds to a temperature of 20 degrees C, which is 293.2 Kelvin. We're going to forecast ln of y, and then we'll convert it to y. So ln of y, I'll put that over here. Ln of y is equal to ln A F4 plus slope of b F4 times x value, which is T, temperature. Enter. So that's forecasts as 3.4 is the ln of y prime, and it automatically calculated a y prime of 29. And I believe that agrees with what we had up here. Yes, it does. All right, and finally, let's forecast the temperature that corresponds to a resistance of 12 ohms, which is what the meter is actually doing when we use it. So that'll be x is equal to ln of y minus ln of A divided by B. So we're going to need ln of y. So the ln of 12, there it is now, we'll use that, equals bracket the ln of y minus ln of A, here it is, close bracket, divided by B. I'm not going to put absolute references because I'm not dragging these, 321.5, and yes, that looks good. Alright, so that's it. This worked quite well, and that kind of wraps up our treatment of regression of all the various types of data. Next we'll move on to solving linear equations and quadratic and polynomials and differentiation integration on the Sharp calculator. Page 243 and 244. Solving 2-variable and 3-variable linear equations on the Sharp calculator. I'm just going to demonstrate how to solve a 2-variable linear equation. The 3-variable linear equation is done the same way. I chose two simple equations. 2x plus 3y equals 4. 5x plus 6y is 7. I chose numbers that were easy to remember as we add them to the calculator. We choose mode. 4 is equation. 0 is 2VLE. A1 is the coefficient of x, that'll be 2, equals, then 3, coefficient of y, then 4. So it's simply number equals, number equals, number equals. Here's the next one, 5 equals, 6 equals, 7 equals, and you get your answer. The point of intersection is x, y. Page 245, solving quadratic equations on the Sharp calculator. We'll just do equation A, y is equal to 4.5x squared minus 1.1x minus 0.5. Press mode on the calculator. Then you want 4 for equation and 2 for quadratic. So enter the coefficient A, which according to the calculator is the coefficient of x squared. That'll be 4.5. Then equals, the coefficient of B is negative 1.1 equals, the constant is negative 0.5 equals, and those are your positive and negative roots. 0.477 minus 0.233. Real easy. On pages 246 to 249, I have instructions for doing differentiation and integration on the Sharp calculators. I'm using the ELW516XG. We'll be taking the derivative of the equation 3/2 x squared minus 6x plus 4 with respect to x at x equals 5. You want to be sure to be in the right view mode. It's just a lot easier to enter your data that way. And so to get there, you should start in mode 0, the normal mode. From there, you'll see me in a moment click second function math, which gets you into the setup mode, and from there you can choose number 2 editor, 0 right view, and then I chose 1 for approximate. Okay, so working from the normal mode, mode 0, press second function math, gets you into the setup. Choose 2, which is editor, choose 0, which is right view, and I chose 1 for approximate. Okay, to start the differentiation, hit alpha and then close the bracket. Alright, we want to put 3 halves, so you need to hit the A over B key. The cursor's in the top, enter 3, arrow down, enter 2. Now you have to arrow to the right and put in the x squared. It's be alpha x. Now to square it, you got 2 options. You can either press x squared or y to the x, then 2. But hold the phone here. So you have to be careful here. If you clicked the x squared key, the cursor is ready for you to enter subtract 6 alpha x plus 4. But if you chose the y to the x 2, the cursor is still up in the exponent after the 2. If you hit the minus sign, it will stay up in the exponent, and you don't want that. To get it out of the exponent, you have to actually hit the right arrow key, brings it back on the normal line, then you continue with subtract 6 alpha x plus 4. But if you chose x squared, do not hit the right arrow key, because that'll dump you right out of the integration. So be careful here. So I chose y to the x 2, and so I'm going to click the right arrow key before I type in the subtract 6 alpha x plus 4. So here goes. Right arrow, then subtract 6 alpha x plus 4, and then right arrow out, and then 5, enter, and the answer is 9. Piece of cake, eh? Finally, we're going to integrate the expression cos of 2x plus x squared over 2 over the range of -1 to plus 8. Start with alpha, open a bracket. Enter your lower limit, -1, arrow key up, upper limit is 8, right arrow, then cos, open a bracket, 2 alpha x, close the bracket, plus, need a quotient here, a over b, alpha x squared, down arrow, 2, right arrow, equals, and patiently wait 30 seconds and you'll get your answer. 94.4 in this case. So that'll be it for our lessons on the use of the Sharp calculator in technical math.